Okay, how to ensure your heat pump is smart grid ready. So these are the types of domestic heating systems in the UK generally. So we've got gas boilers, gas and LPG boilers, heat pumps, electric heating via direct panel heaters, and oil central heating. I mean, this presentation is mainly to do with the domestic sector, but it can be carried over to industrial or commercial sectors. That the principles are very much the same. So this is just a little bit about how heating systems compare with regards to efficiency. So we can put them all on a level playing field. We've got gas and oil boilers. You put 1 kilowatt of electric in. If they're A-rated boiler, you'll get approximately 0.9 kilowatt of heat out. So they're 90% efficient. Electric heating system, such as panel heaters or storage heaters, you put 1 kilowatt of electric in and you get 1 kilowatt of heat out. So they're known as 100% efficient. And then lastly, we have electric heat pumps, where you put 1 kilowatt of electric in, but because you get 2.5 kilowatts of free heat from the ground or air, then you end up with 3.5 kilowatts of heat. So they're known as being 350% efficient. So that's their efficiency, but how do they compare with regards to running costs with each other? So we have mains gas, which is actually the lowest form of heating cost, with a boiler efficiency of 85%. LPG and oil heating, the rural properties, they tend to be higher. Direct electric panel heaters is by far the highest cost electric when looking at standard tariffs. And then we have heat pumps, even though they're very efficient. I've got a SCOP here at 3.25, which is pretty average. They're still slightly above a mains gas boiler, which is quite surprising. But that is to do with the cost of electricity and gas in the UK. So even though heat pumps are very, very efficient, because the cost of electricity, we can see here, I mean, these were taken some 7 or 8 years ago, but the trend is pretty the same. The cost of electricity will always be, or has been, probably for the foreseeable future, 3 to 4 times more expensive than gas. So heat pumps lose out a little bit because the cost of electricity is so high. But what's changing in the UK? What's the future for the price of electricity? So we'll soon see, well, we are seeing at the moment a decline of single rate electricity tariffs, and they're getting replaced by the surge in smart tariffs, helped by the mass rollout of smart meters. We're going to see more and more of these tariffs coming in. It's only the innovative energy suppliers at the moment, but the big players like EDF, Scottish Power, they'll start bringing these in. So this example here is one from Bulb. This shows their smart tariff, so you need a smart meter for it to work. And they offer cheap electricity overnight, in the day, at reasonable rates. But if you use energy in peak hours from 5 till 8, then it's an extortionate 41.4 pence. Again, in the evening, it's a reasonable 11 pence. But you can see that their standard tariff, so if you were just on fixed, you'd be paying that 14.25 on that line. But if you can make use of using energy at these off-peak rates or super off-peak rates, such as overnight, 7 pence is half price, you can make substantial savings. And this isn't any different to the analogy at the bottom here. I've got rail fares. So in the middle of the day when it's quiet and there's no one on the trains as much, we pay off-peak fares and they're very cheap. Comes to 4, 5, 6 o'clock when everyone's finished work, we have peak fares because everyone wants to get on the train. So it's a lot to do with supply and demand, and electricity is very much like that. From 5 till 8, we haven't got much electricity, so the cost of wholesale price is high. So how can heat pumps exploit this new way of buying electricity? Heat pumps, they can be designed to generate and store heat with super low electricity. Buffer cylinders can be used as batteries to store heat. On the example on the right hand side, we have a ground source heat pump. We always need to fit a buffer, so this is a perfect way to be used as a battery. Underfloor heating systems can be used as to store heat in the screed. There's new innovative thermal heating batteries. They can be utilised to store heat where it's premium. And then heat pumps themselves, the manufacturers are gearing up to be set up smart grid enabled. So this is one manufacturer here who has set up some API so that can work with weather forecasting, smart meters integration. So it really is smart grid ready. So what effect running heat pumps on smart tariffs has on the running costs? So we saw earlier that heat pumps didn't really, was very simple, whereas this shows a smart heat pump with a weighted tariff of 8p a kilowatt hour, similar to bulbs. With a SCOP of 3, we're actually getting down to just over 2p a kilowatt hour, which is it's 50% cheaper than running the heat pump on a standard tariff, and more interestingly, it's actually 40% cheaper than mains gas. Mains gas just over 4p. So we can see that running a heat pump on a smart tariff has massive advantages over the other fuels. So this is just a case study now, a trial of a heat pump controlled by a smart tariff that we put into this home. Brick built, quite modernish home, cavity wall, loft, double glazing, so standard UK sort of house or bed. So what we did, we put a heat pump and a special retrofit underfloor heating system, so there was no digging out the floors. So we needed to look at getting some sort of thermal storage in there. Radiators don't work so well with a store, but storing heat in screed is a very good way of storing low cost energy. So we fitted a 20mm retrofit underfloor heating system with this high density screed, and this is just to show you a quick example of it going in. Okay, so that's just an example of the underfloor heating going in, very low profile, just playing off the doors, and all of a sudden you have a very good underfloor and a way of using heat into a battery, a thermal battery type. So just a little bit on the screed now. So hats can, like this one, map by Ultrapan Maxi, a very dense screed, so it can store a lot of energy, even at a 30mm, which isn't much. If you see this example on the left-hand side here, so this is the idea. We're running heat through a network of underfloor heating pipes, and in turn that is giving off its heat to the screed, which is heating as a slab, and then that radiates through to through the floor and into the room. And just a quick example of the type of resin screed that we install. It's mixed, and so it just gives you an idea of the job in hand. Only a 2-day install. So these are the settings of the heat pump now, of how we use the heat pump to work with the smart tariff and with the screed. So what we did, we used Octopus Go, which is a tariff where it's 5.5p per kilowatt hour for 5 hours overnight from 1:30 till 6:30. So the heat pump is designed to charge up the screed in this low off-peak time. The peak rate on this tariff was nearly 15p, so it was geared up to use as much as the low rate as possible. So we can see on this graph, this is what was happening when the cheap rate kicks in. The heat pump kicks in, heats up the screed, uses all the cheap energy at 5.5p instead of 15, so it's super cheap. But then, because that wasn't lasting the whole day, the heat pump was programmed to provide a further boost at approximately 3 p.m. in the afternoon, and which we can see here. This is the second boost of the heat pump using electricity to convert into heat to just lift the temperature back in the house back up. And this was a day in January, 18th of January, so a pretty cold day. Some days the heat pump was able to just use energy here but because of the heat loss in the house, they needed a second boost here. So this was using peak electricity, so 15 pence. But the idea is to use most of the energy here. So this is just to touch on the comfort in the home and how it provided heat to the home. So this was a graph from the underfloor heating controls. So the orange is the average indoor temperature, and the blue is the outdoor temperature. So the aim of the game is to have the temperature at 21 degrees. So what we're doing with the screed, we're letting the screed heat up to 22 and roughly fall back again to 20 degrees. So it's not too cold in the house. So we can just see here as an example. So 6 o'clock in the morning, the heat pump's really ramping up, and because there's a lag on underfloor heating, even though it's heated up at night for 5 hours, you don't see that effect till 9, 10 o'clock, 11, throughout the day. And that's quite important. So it actually suited the property quite well, because it was able to give heat when it was needed. So here we can see the peak, and then slowly going down again. I think we can annotate there. So that's when it's losing its heat, and that's when it's having its second boost. Heat up again, and then falling again, heats up again at night on the super low rate, fall again, heat up again. But the idea is to use all the energy at the night rate as much as possible. A few other things we did, the screed temperature was heated to 27 degrees at heated times, and floor sensors were installed to ensure, we need to make sure the surface temperature of the floors didn't exceed 27 degrees, because a lot of floors don't like you to exceed that level. Okay. Clear. Okay. So the case study continued now. Running costs over a year. The heat pump used 5,500 kilowatt hours per annum, so approximately 85% used at the super low rate. So we can see here that on a standard tariff, the heat pump would have cost £825 to run on a standard tariff. But because we implemented the smart tariff and the run times at night, for instance, we were able to get a weighted purchase energy rate of just over 6.5 pence a unit, because some was bought in at 5 and some at 14.63, I think it was. But the average was 6.5 pence, which meant the cost of running this heat pump was £385. And that was a saving of £440 just by using the smart tariff combined with the underfloor heating screed. Okay, so that case study used the underfloor heating as its battery. You can also investigate oversizing buffers. They can be a low-cost way to store heat. So in this example, we've got a smart meter linked with API controls. So if we run the heat pump on 5 pence per kilowatt hour, the heat pump's 300% efficient. We can quite easily store energy at 1.6p per kilowatt hour, which is a very, very low source of heat compared to mains gas and other sources of fuel. Nothing really touches it. And that's simply if you divide 5 by 3, and that's what you're doing with the heat pump. So even when you run at a higher temperature, 55 degrees, for instance, because heat pumps can be set up, the smarter heat pumps that know when electricity is cheaper, they can run at a higher temperature. So that in this example, it's running at 55, it's keeping the buffer at 50 degrees, but we only need sort of 30 degrees in the underfloor heating system. So you need to store at a higher temperature here to make sure we've got enough storage, enough energy to run at the lower temperature. And in this case, we're actually mixing down on the manifold to make this sort of storage last a lot longer. Okay, so the use of thermal batteries. So this is a job that the previous buffer cylinders, thermal stores, because we're storing water, we need a lot of space in the property. And these thermal batteries are an innovative idea. They do the same job as a thermal store, but they use a phase changing material inside. So we're not heating water, we're heating up this material, which is storage. So it means a lot more compact and a lower standing heat loss as well. So with a thermal store, if we've got 1500 litres of water, that's going to be quite a high. That could lose maybe 7 or 8 kilowatt hours a day, whereas if this equivalent storage in a sun battery would be a lot less standing heat loss. Main disadvantage is the higher cost compared to a buffer cylinder. Very expensive at the moment compared to cylinders, but if you haven't got the space, then they are the idea. So you could have a combination of thermal store and screed. In this example here, we've got a ground source heat pump, again, low cost electricity. So we've got two types of batteries. We've got a thermal store, just say in this example, can hold 30 kilowatt hours of storage. And we have the underfloor heating and screed, which might be able to hold 20 kilowatt hours of storage. So this is just a touch on design. It gets more complicated than this, but if the daily space heat load for this home was 50 kilowatt hours, then we can almost quite comfortably charge the batteries up with 50 kilowatt hours of heat to provide heat for the whole day for this property. So if we've got 50 kilowatt hours of heat and we've got a 12 kilowatt hour heat pump, we need to have a smart tariff which can last for 4 hours for this to work. So in this example, it'd be 4 hours at 5p. So that is the ideal scenario. So smart heat pump, is it a smart investment? Well, this is just to touch on the installation costs of a ground source heat pump example. So with the standard setup, you're probably already looking at in the region of sort of 17,000 for an average heat pump. But to enable it to be smart, and that could be choosing a heat pump with good controls, smart controls. It could be fitting a larger buffer cylinder, could be fitting a heat battery, could be installing slightly more screed to use the battery. But if we call the average cost of £3,000 more to make it smart, that's quite minimal in the scheme of things. And we already saw from the last case study that there was £440 saving in the first year. So if we look at that over the lifetime of the heat pump, which is 25 years, we can save £11,000 on running costs, which is a profit of £8,000 on the initial cost of £3,000. So, and that's on smart tariffs alone. There's other ways we can save money, but that's just on smart tariffs alone. So once you've designed a smart ready heat pump, the benefits are endless. There's different things you can do. So once you've got the battery, the thermal battery, the thermal store, or the screed, or the controls for the heat pump, you can benefit from the lower running costs, as I've mentioned before. It can integrate with other technologies such as battery storage. So in this example here, we have the battery storage system. So this is a Tesla Powerwall. So this is charging on off-peak electricity here at night again, and then it's providing energy for the home in the morning. And then this particular property was coupled with solar. So then the solar then charges the house and battery, and then the battery discharges to the home and the heat pump in the evening. So in this example, we're using all the energy overnight on this Octopus Go tariff. They were on, and I'm not using any energy in the day, and that really is the aim of the game, because if you can buy energy at 5p or 6p, you really are saving a lot of money compared to buying energy on a standard tariff. Some other benefits: you can earn income through negative energy prices. If the system is set up, this is becoming more and more now. So we're seeing negative energy prices, which are quite difficult to get your head around, really, because we've been buying energy as normal for the last 70, 80 years, or however long it's been. Now is the time where we're seeing energy companies paying through smart meters consumers for using energy. I mean, it's happened in industry for some time, but domestic customers are actually seeing being paid. So in this example, customer was paid 5 pence per kilowatt hour for every unit you use in the morning for 2 hours. So you can see if you had some sort of heat pump with a hot water cylinder or some sort of storage, you can actually be paid to provide heat for your home. So it really is quite exciting, really. The other one that's coming through now is there's potential revenue you could earn through demand side response. There's a lot of trials going on with demand side response and electrification of heating systems at the moment, and how they can be used to help the grid be more flexible. So that in the future there might be times to help the national grid out. You might be asked to switch your heat pump on. So the more store you have, or the more excess you can get rid of, the more you'll be actually helping the national grid. So a smart heat pump is a very smart, very positive for the environment. On the right hand side, this graph, this is showing actually just general heat pumps in general, not talking about smart tariffs. But we can see electric heating on its own and gas very similar at the moment, and they're emitting about 250 grams per kilowatt hour of emissions. But the great thing with heat pumps, we can see here at different COPs. So this is the efficiency of the heat pump. So we can see a COP of 4 is a greater heat pump efficiency. So it's far less carbon emissions than gas or electric, and that's even just without talking about smart meters. But a smart heat pump can help stabilize the grid. Smart heat pump, it can help to I might have touched on this earlier, but this graph, and sorry for all the graphs, but the important thing about this one is from Drax. This was on the 24th of May, so Sunday. The price of electricity here, this is the most important thing, actually went negative to £65.94 per megawatt hour, which is equivalent to about 6.5 pence a kilowatt hour. Now that is quite alarming, really, that the energy suppliers are actually paying so much to get rid of their energy, that there was a glut of solar and wind, and coupled with low demand, and this is going to happen a lot more often. We can see the emissions actually at the time were 24 grams per kilowatt hour, which is absolutely minimal. So if we can have enough heat pumps to take this power and to use it flexible, this is going to be the way forward. I mean, if we had, if 20-30 million gas boilers aren't going to help with this problem, gas will never sort of help with this supply and demand problem, but electrification, heat pumps can really help with the national grid. This is just to talk about it is a tried and tested technology, this idea of storing heat through electrification. Storage heaters have been around for 50 odd years, and they were designed with the economy 7 tariffs to heat up overnight for 7 hours, mainly for coal power stations in the 70s and 80s that couldn't turn off very easily. It was far cheaper for them to actually give the electricity away for half price, and for people to store up the energy in their homes. So the idea of what I've been talking about has been tried and tested, and has worked very well. The problem is with the UK, we generate a lot of wind. There's a lot more wind and solar coming online, and we don't know exactly when this energy is going to be providing power. We can't you can't predict the wind, so that when that is really running hard, we've got a lot of energy, as we saw with the negative electricity prices. And because we're an island, we can't really get rid of our electricity. We've got some small interconnectors, but compared to Germany and France, we do struggle to export a lot of our energy. So a lot of the time it can be wasted. So how can smart heat pumps roll out to mainstream? I mean, there is some advantages, but it needs a collaborative working. Everyone needs to work together. So we've got the manufacturers need to look at their heat pumps, get better API forward weather compensation controls built in, so they can talk to smart meters. Installers have got to get genned up on all, instead of designing for the run-of-the-mill standard heat pump, explore smart tariffs. Developers and designers, it'd be good if it was written into some specifications. And this is quite an interesting. Clients and end users have got a massive role to play in it. So for example, an installer could be pushing it, a manufacturer could be ready, but if the client isn't ready to move on to smart tariffs or engage in smart meters, and look at different tariffs and how they can save money, but then the whole project won't work. Government policy, again, we can see helping the heat pumps help the grid. There's a lot of money to be saved, carbon to be saved, so government have got to push on, you know, trying to make get it into people's homes, factories, businesses. And then we have utility companies who need to, we've got Bulb and Octopus and some of the innovative tariffs to do with smart tariffs, but it's not really at the moment. Most of these suppliers aren't really providing them, so utility companies have got to really start making heat pump tariffs friendly, smart tariff, be doing more. Okay, so that's thank you for listening, and any questions. Apologies for all the graphs and figures, and if I ran through it a bit quick, but any questions? I'll be glad to answer.
Thanks very much, David. I've been noting the questions that have come in the chat. Quite a lot of comments, and so what I'm trying to do is summarise some of the discussions for you, and perhaps ask you to comment a little bit further, David. Is that okay?
Yeah.
So Roger Macklin makes the very pertinent point that you've got to be careful in saying storing energy in an underfloor system, because that has the implication that you could perhaps recover that energy and use it somewhere else. So I think that's just really a comment on that. Would you like to make any points on it?
I mean, obviously in the summer, it's a boiling day today. It's not really going to be a day like today. You're going to be storing energy in underfloor heating, so it's mainly looking at the winter. It's a very good way of storing energy in a screed. I'm not sure what he means by going anywhere else.
I think Roger's making the point that we're using the underfloor, the screed, as a thermal mass rather than as a thermal store.
Yes. I mean, yes. I mean, they're very similar in a way. I mean, I say that the underfloor heating is like a thermal store. Yes, you're right. It is a thermal mass as well. So yes.
Okay. And there's just a couple of other comments on that makes the definition between a buffer tank and a thermal store. So
oh yes, okay. So yes, I think in my slide I did call it two different things. So apologies for that. There is essentially the same thing. A buffer cylinder is a thermal store. It's just a volume of water that can be heated up and hold heat. They're sometimes called a buffer. Generally with heat pump designs, you're calling them buffers. But yeah, I was calling it thermal store. It's slightly easier way to understand.
I think Roger makes the point that a buffer tank is primarily there to avoid short cycling on a heat pump, whereas a thermal store will achieve that and will be sized to store a significant amount of energy.
Yes, you're right. Buffers are primarily there for short cycling, but there's no reason you can't use a buffer as a thermal store.
And then finally, there's a point made by Roger again that the data available on the carbon intensity of the grid is now really good. And I just posted in the comments for everybody the link to the Ground Source Heat Pump Association's very nearly real-time comparator, which is available on the Ground Source Heat Pump Association website.
Yeah, that's right. I mean, it's changing all the time. I mean, that information, it's changing daily. I mean, it can change hourly, and it can be very low. It can be as low as zero quite often. So yes, you're right. It's the trend is it's going down and down. It used to be very high maybe 10 years ago, and we're getting to the point where it's very, very low. So it's more of a advantage for heat pumps to run on this low carbon electricity.
Okay. So just a question coming from Bean, or the Ground Source Heat Pump Association chair. He asks, does the use of underfloor heating screed equate to the concept of preheating that is being discussed more and more?
Preheating, not sure. Can you elaborate the question?
Charlotte, could you let Bean talk?
Yeah, here I am. Yeah, no, it's just interesting to hear what you and everybody else had to say, because the concept of preheating buildings to smooth out peak demands is being increasingly talked up. I just wondered whether you and those on the call, on the those listening into the webinar, would advocate preheating using whether using the screed and the therefore the thermal mass, the inherent thermal mass of the building is effectively it's a preheating format. Yes.
Yeah, so that's why I struggle to answer the question, because that's exactly what I thought. It's exactly the same thing, really. Preheat or store are very similar ideas. So yes, it can be used as a preheat.
Excellent. Thank you, David. Do we have any more questions? Okay.
Great. Well, thank you very much. And yeah, on behalf of the Ground Source Heat Pump Association, thanks for listening.